Hey there, chemists. Welcome to today's lesson. Today we're going to be talking a little bit about what is called thermochemistry, our next unit. It's one of my personal favorite units, and I bet you can guess what it's about based on just the term thermochemistry. But before we jump into our notes for today, I did want to start today with just a quick video to kind of demonstrate a little bit of the concept behind thermochemistry. So here we have water, sodium hydroxide, ammonium nitrate, and sodium chloride. Note that the temperature of the water is 20 degrees Celsius. When the water is added to the first beaker, we're going to add the sodium hydroxide to that beaker. Okay, we're going to give that a good stir, and we're going to take the temperature of our solution. And notice that the temperature of the solution is now 48 degrees, so from 20 to 48. The same is done with ammonium nitrate. Our solution is now 8 degrees, so 20 degrees to 8 degrees. And lastly, for sodium chloride, we're going to do the same thing. We're going to give that a nice mix. And we're going to go ahead and take the temperature of the sodium hydroxide, of the sodium chloride, and the solution's temperature, not significantly impacted, but it is 22 degrees. So this is interesting because in the process of dissolving these three salts, we've changed the temperature drastically for two of the three, sodium hydroxide and ammonium nitrate. So what I want to go ahead and do is I want to go ahead and go to our notes sheet for today. And I want to go ahead and jot down those two reactions that we saw. So what we were looking at here was the dissolution or the dissolving of two different salts. The first of the two was sodium hydroxide. So to go ahead and write that, we have NaOH solid. And water is not part of the reaction, but it is used to dissolve the substance. So we're going to go ahead and add our water. And we create two different ions. We create our sodium ion in the aqueous format, and we create our hydroxide ion also in the aqueous format. Now, something that I also want to go ahead and record was our initial temperatures. So the initial temperature initial, was 20 degrees Celsius, and our temperature final for this was 48 degrees Celsius. Excellent. The next solution that we saw was ammonium nitrate. So that's NH4NO3 solid. Excuse me. And we went ahead again and dissolved that into water. And we produced ammonium ions, NH4 plus aqueous, and nitrate ions, NO3 minus aqueous. And I want to go ahead and record, again, our temperature change. So our initial temperature of the water was 20 degrees Celsius, and our final temperature was 8 degrees Celsius. So the question is here, why do certain solutions become warmer when the salt is added versus why do some get colder? And this leads me into just defining what is thermochemistry. So thermochemistry, maybe you were able to break it down. Thermo, the base, is going to be the branch of chemistry which studies heat absorbed or released, okay, during any process. So again, looking at the word thermo, that literally means heat. So thermochemistry is the study of heat chemistry, okay? There are two types of reactions that can occur, okay? There is endothermic reactions or exothermic reactions. Endo versus exo, we also use the base of those words to help us remember the two. endothermic reactions are going to be reactions which absorb heat. Okay? And the way I like to remember this is endo, N, that beginning of that is literally like heat is entering. So endo is heat is entering the system. Which leads us to exothermic reactions. Again, use the base of that word. Exo is like exiting. And these are going to be reactions which release heat energy. Okay? So before we can talk about which of the examples we saw up top were endo versus exo, you might be able to guess, but it's also really important to talk about the system versus the surroundings, because anytime that we are talking about whether something is endo or exothermic, we're talking about the system and not the surroundings. But all of our reactions are actually measured using indirect measurement. And so an example of this, maybe a little bit easier to see than the salt dissolving that we saw, would be something like a hand warmer in a coffee cup calorimeter. So this is my terrible drawing of a coffee cup calorimeter. I am no artist. We have here our thermometer, we have our water, and we have our reusable hand warmer. So this here is a hand warmer. Now, in this calorimeter, a calorimeter is used to measure heat, okay, in a reaction. And oftentimes we use coffee cups because of their insulation properties. So there are obviously some issues with thermochemistry being done in a classroom or even in just like a nice open air lab, because we will have some heat lost or gained during this process if it is exposed to the environment. And so part of what doing this in a coffee cup calorimeter does is insulate that water from the outside surroundings, so that heat is not lost or gained, as well as using water. If you think back to the last time we talked about heat, water has a fairly high specific heat capacity. So it does take effort, or I'm sorry, it can absorb a decent amount of energy before the temperature changes. So when we use the water, it allows for that direct transfer of heat from the hand warmer to the water and absorbs the water, but it probably will absorb very little heat from the air, okay, or lose heat to the air. It takes time. So let's talk about system versus surroundings. So in this instant, and really anytime we're looking at thermochemistry, we are always talking about it in terms of the system. So I do want to go ahead and make note of that down here. So anytime that we are referring to endo versus exothermic processes, is always in terms of the system. And you'll see why that becomes important in just a moment. So in this instance, we're interested in studying how much heat energy is released or lost or given off by the hand warmer. So in this instance, okay, our system is the hand warmer. Okay, so this is our system. It is the hand warmer. Okay, and the system is the substance or object, okay, we are interested in investigating. Okay, versus our surroundings, which is the water in this case. And in calorimetry, we use the surroundings to measure the heat being released or absorbed by our system. Okay, and we're going to use, this is going to be how we're going to measure it. And that's why this is an indirect measurement, right? We are measuring how much heat energy is being released or absorbed by the hand warmer. But we're going to measure it by making measurements in the water, not directly from the hand warmer. So it's an indirect measurement, but again, water is so useful because of its high specific heat capacity. So this is important because if you are familiar with hand warmers, they are used literally to do exactly as we would think, to warm our hands. So does a hand warmer give off heat energy or does it absorb heat energy? And the answer is that it releases heat energy. So the hand warmer is going to give off heat energy to the water. So let's make a statement together. In terms of the hand warmer, the reaction was exothermic because the hand warmer releases heat. Okay, and the reason, again, we have to distinguish that it's in terms of the system, and the reason that I took the effort to point that out to you guys is because think about it this way. If the hand warmer is giving off heat, what is happening in the water? Is the water absorbing heat or is the water releasing heat? So if the hand warmer gives off heat, then that means that the water is absorbing heat. So the water will absorb all of the heat energy that the hand warmer gives off. And so our water is endothermic, but our hand warmer, which is what we're interested in studying, is exothermic. Okay, so how do we then put numerical values to the amount of energy that was released by the hand warmer? I'm not going to use a thermometer to directly measure my hand warmer, mainly because, again, we're using this indirect measurement. We're going to use the temperature change of the water to help us understand the amount of energy being released by the hand warmer. And so we're going to use a familiar equation to help us calculate that value. So let's calculate the amount of heat energy that was absorbed by the H2O. So Q equals MC delta T, right? Think all the way back to when we used that last, is our equation we're going to use. So we're going to be solving for the Q. Our mass, I'm going to use some just theoretical data for this. Let's assume that we used 100 grams of water. The specific heat capacity of water is 4.18 joules per gram degrees Celsius. Our initial temperature, let's say it was 25 degrees, good old room temperature, and our final temperature was 30 degrees. And again, we're doing this hypothetical data for this hand warmer experiment. So let's go ahead and calculate how much energy was absorbed by the water. So we end up with Q equals MC delta T. Q equals 100 times 4.18 times delta T, TF, remember that's TF minus TI. So we're going to get 30 degrees minus 25 degrees. Okay, and our Q value here, let me just calculate this really quick. So 4.18 times 100. Okay, times 5 gives us 2,090 joules of energy. Now, this is the energy that was absorbed by the water. I want to note something here, and I'm going to scroll back up. You're going to go back to the top of your notes in just a moment. Notice that when we're talking about absorption of heat energy, our Q value is positive, okay? So let's go back up to the top really quickly to our definitions of endo and exothermic. And I want to note that when we have an endothermic value, our Q is positive. Okay, we have a positive Q, which means that when we have something that's exothermic, our Q value is going to be negative. Okay, so the question then becomes, again, we're not really interested in the water, we're actually interested in the hand warmer. So how do I determine that value? Oops, really quickly, let's take a look here, sorry. So question, how does our calculated Q support water absorbed energy? Again, Q is positive. Okay, and we know that because the delta T was a positive value, the water absorbs heat. Okay, and now gets to the good question, which is how do we determine the amount of heat released by the hand warmer? Well, we can use a theory that we've talked about a couple of times here. The theory is the law of conservation. Okay, and the law of conservation states that all the energy that's absorbed, right, is released by something else, or energy is not created or destroyed, but simply changes form. So all energy absorbed by the hand or by the water was released by the hand warmer. So how much energy was released by the hand warmer? Well, we used water to figure it out, but we know that the Q of our hand warmer is negative 2090 joules. They are equal, but opposite in sign. All right, everybody, one last quick thing. I'm going to save the practice problem for in class tomorrow, but I do want to go back up to the top and just take a look at our two reactions that we saw and to decide if those are endo or exothermic. So in this instance, again, we measured the initial temperature of water and the final temperature of the solution. So in this instance, the water increased in temperature, so the water absorbed energy, which means that the NaOH released energy, okay? So is that endo or exothermic? Okay, that is exothermic. In this instance, the water released energy to the salt. We know that because the water temperature decreases, which means that the NH4NO3 absorbs. Okay, therefore this is endothermic. All right, everybody, I know it's a little long. I'm sorry. I hope you guys have a great rest of your night, and I'll see you tomorrow.